The new chapter, chapter number 9, is areas of parallelograms and triangles, which we're going to deal in today's session. Parallelograms and triangles. We have dealt with various properties in quadrilateral, special type of quadrilateral called a parallelogram and a triangle. Now comes the deep investigation on areas of parallelograms and triangles. Today's session is about investigation of triangles and parallelograms with their areas. Before we get into the areas of parallelograms and triangles, let's come with the introduction. Introduction. Let's recap with geometry. We have previously come out with the concept of geometry, which was referred as geo plus metry. That is, geo stands for earth and metry stands for measure. So measure of earth or measure of the agricultural fields or measure of the land is what from which geometry has originated. So this problem was existing in prehistorical facts that many agriculture fields or lands were supposed to be divided among the children or the next ancestors. So division of land to be done equally among all the sons or daughters was a difficult task during those times. So geometry was very much in use during those times. In order that the land be divided equally, many of the people used mathematics proudly. So here comes the introduction of measure of earth connected with areas of parallelograms and triangles. To continue with, imagine I have an agriculture field which is triangular in shape. Imagine this is my plot and this is the plot of land which I want to divide equally among three people. Like for example, say Budhia was a farmer Budhia wanted to divide his triangular piece of land into three parts so that he wanted to distribute the land for his two daughters and one son. So how can he distribute this triangular piece of land equally to the two sons and one daughter without any disputes? This to be done mathematically. So such problems give us an indication that we need to give more importance to areas of triangles and of course areas of parallelograms. So here Budhia has tried to cut his land out here and then he tried to cut his land from each corner to some part, estimated part in the middle. He wanted to cut his land in this region. Now after cutting his land into three parts in this manner, he wanted to give this to the first piece to his first son, and this piece of land to his second son, and this piece of land to his daughter, who is third in number. Now he assumes that these three areas are equal. According to Budhia, his estimation that from the center of this, approximately the cutting of the land to each of his vertices of his agricultural land, A, B, C, are assumed to divide the whole triangular piece of land into three parts, first, second and third. And according to Budhia, area of the first piece is equal to area of the second piece. Though they are in different shapes, it is assumed that area of the first piece, according to Budhia, is equal to area of the second piece, and also this is equal to area of the third piece. Is how we understand each of the areas being equal. Thus, the two sons and the daughter would happily share the land without any disputes. But here the biggest question comes: how do you prove mathematically that these three are equal? Is it that they are just convinced that they are equal without any proofs and justifications? Or is it that really Budya could justify the three pieces of land exactly in equal areas? Here comes the investigation in mathematics about how we can find the areas of equal pieces within the triangle. Is how we are going to connect in the future coming topics. Budya's problem related with area of triangle subdivided into areas of three different pieces of triangles. Now that we have investigated on Budya's case of a triangular field arising in to the conclusion that we need to give importance to areas of planar regions or areas of regions, mostly the lands, without any dispute. Now comes, what is area? How do we define area in the branch of mathematics? So let's see in today's session about area and its mathematical properties. So here comes area. What is an area? So let's see in brief area. Now imagine I have a closed region. I have a closed region. So this region is closed in all directions. So such a region which is closed in all directions is called a planar region. This is a planar region. So this planar region has area, which is called the magnitude or measure of this planar region is called area. That is the entire boundaries within whatever region is covered, we call that as magnitude or measure of the planar region. So in simple manners, area is defined as the magnitude or measure of the planar region. Is called area. Is how we define area of the planar region. A close-sided figure whose magnitude or measure which accounts to area. The magnitude or the measure of the planar region is how I define area of the given region. Area of triangle, area of parallelogram, area of quadrilateral, and area of various other things is how we understand. The magnitude or measure is always expressed in a number. That is, the area, which is the magnitude or measure of planar region, is generally given in count of numbers, and the value of the number will define the size of the area. So this is a very important note. The area is generally counted on numbers. That is, area equals 3 centimeters square or area equals 15 centimeters square, etc. Now here this implies that if the area is 3 centimeters square and area is 15 centimeters square, that means the second area is bigger than the first area. Is how we estimate the magnitude or measure of the planar region through the value which is assigned to the area. And these are the units given for area. Is how we understand the area connected with the planar region. Now that we have discussed about area connected with planar region, now comes congruency of two figures. If I take two planar regions or two closed figures, let's see what congruency stands. Today's session is about congruency of two figures. So let's take two figures. Say I have a figure and this figure too. Now I have two figures out here, this being in this manner and this being in this manner. Now the question comes on defining congruency of these two figures. What is congruency of these two figures? Congruency of two figures, these two are said to be congruent. This is figure 1 and figure 2. Both the figures are said to be congruent if they have same shape and same size. Imagine this is in this form, and if I rotate this to the top, also it has the same shape. This is indirectly understood to be in the form is how I understand this in this form. So this connected with this when this is rotated into this. So this is exactly the same as this. So congruency of two figures is when they have the same shape and of course the same size. So here I define two figures are said to be congruent if they have same shape and size. Is how we define the congruency. Congruency of two figures. Two figures of same size and same shape are said to be congruent. This is congruent to this. But this is not congruent to this because they are of same shape but they are not of same size. Since not of same size. Since they are not of same size. Therefore, this is being of smaller size and this being of bigger size, though they are of same shape, cannot be congruent. Is how we understand the congruency of two figures connected with same size and equally same shape. Now that we have defined the congruency of two figures, now let's see how we can connect congruency with areas. Two figures are said to be congruent if they have same shape and same size. Then what will be the status of their areas is what we are going to define in today's session. Congruency connected with areas. Now that we have defined congruency, let's recall the definition. Congruency is connected with same size and same shape. Now it is generally assumed that if two objects or two figures are of same size and same shape, mathematically it is proved that they must be of the same area. So here comes the conclusion that if two figures are of same size and same shape, then mathematically they must have the same area. That is, the measure of their planar region or the magnitude of their planar region must be same. Is how we define the property. Therefore, when two figures are congruent, not only did they have same size and same shape, they have same area. So I come to the conclusion that two congruent figures have same area, is how I conclude the statement. Two congruent figures have same area is the learning outcome, and congruency connected with areas. Now that we have connected areas with congruency, let's come with the converse of connecting congruency with areas in a similar manner. So what does the converse say? The converse is about if the two areas are equal, will the two figures be congruent? Because in the previous session we have seen that if the two figures are congruent, then their areas must be equal. Now the question comes, if the areas are equal, will the two figures be congruent? Let's investigate the congruency of two figures connected with areas. As converse. So my question here is, if the two figures have equal areas, then will the two figures be congruent? Is the biggest question out here. So let's investigate this. If the two figures have equal areas, then will the two figures be congruent? So imagine I take a triangle whose area is, say, 12 centimeters square. And imagine I have a parallelogram whose area out here is also 12 centimeters square. Now clearly we know that the area of the triangle is 12 centimeters square and area of the parallelogram is 12 centimeters square, and therefore the areas are equal. So I find the areas to be equal for both the triangle and the parallelogram. But are they congruent? Let's see if triangle is congruent to parallelogram. The congruency concept says that the two figures are congruent if they have same shape and same size. Now here comes the question on the triangle and parallelogram have same size because their areas are same, but are they of the same shape is also very important in ruling out for the congruency. In justifying the two figures to be congruent, we have to justify on same size. Yes, of course, they are of same size, each size being 12 centimeters square, but are they of the same shape? No, this is a three-sided figure and this is a four-sided closed figure. So they're not of the same shape. It fails with the second case. This is a three-sided figure and this is a four-sided figure. Therefore, they are not of same shape, but they are of same size. Therefore, I come to the conclusion that if the two figures have equal areas, as in the case of triangle and parallelogram, then the two figures may not be congruent. Not always. They are congruent if it satisfies with the condition that the two figures have the same shape. Failing with the condition here, three-sided and four-sided figures can never be of the same shape. Therefore, my learning outcome or the conclusion out here is that two figures with equal areas need not be congruent. Congruent. Is how I conclude two figures with equal areas need not be congruent. Is the conclusion in the converse. So the converse of the congruency statement says that two figures which have equal area need not be always congruent, just in the case of triangle and parallelogram. Now that we have defined area of any planar region and connected with congruency of two figures in brief, now let's see how we are going to represent area, because we're going to solve many problems where areas are involved. Now comes the question on how do we represent area of a closed region. Representation of area is the session about. Representation for area. Now let's take this is the region, say, of the planar region. Now I would like to find area of this region. Now how do we represent this region with area? If this is represented by A, this whole region is represented by A, then area of region A is denoted by area of A or AR of A. So simply when I write AR of A, that implies it is the symbol or representation for area of A. So area of region A is denoted by AR of A. Similarly, if I take a triangle ABC and I take the height and the base to be 5 and 2 centimeters, then to find area of this triangle, for example, with altitude as 2 centimeter and the base is 5 centimeters, then area of triangle ABC is denoted by area of triangle ABC. Is how I denote this. Area AR of triangle ABC implies area of the triangle ABC as denoted with this region. Is how I understand area of the region, which is nothing but half into base into height, 5 centimeter square. Therefore, area of triangle ABC is 5 centimeter square. Is the representation when you find area. Finally, I represent the answer with AR of the given region. This region is triangle ABC. This region is A, which comes here. AR of A implies area of the entire region A. Is how I understand the representation for area of any given region. Now that we have defined the representation for area for the region A being AR of A, let's see how we can connect this with congruency of two figures. So as the representation is understood for this region A, I have the property which says for congruent figures A and B. Say I have two regions A and B which are congruent. For those congruent figures A and B, I understand the property as AR of A is equal to AR of B. Is how I understand the congruency. For congruent figures A and B, AR of A equals AR of B, because when two figures are congruent, their areas are equal, their sizes are equal, their shapes are equal, and hence AR of A equals AR of B, the representation of area for congruent figures. Now that we have defined the representation of areas, now let's see how we can connect non-overlapping planar regions connected with the areas. Suppose we have non-overlapping planar regions. The session non-overlapping planar regions. Let's see what are non-overlapping planar regions. Now here, the word overlapping in the sense trying to join the two planar regions without overlapping each other. So let's see in brief the non-overlapping planar regions. For example, I have these two regions which are separated here. So I have two regions here. This is region A, which I denote with say some P, and this is region B or region Q, which I denote. So I have two regions here. This is region 1 as denoted by dots, and this is region as denoted with this. Now I have two regions. The first region region 1 and this being region 2. Now these two regions are joined together such that they do not overlap. Now the planar region 1 denoted by P and the planar region Q denoted by planar region 2 denoted by Q are now joined together, where the whole region joined is denoted by T. If T is the total planar region, if T is the total planar region which joins both P and Q, which joins both the region 1 P and the region 2 Q without overlapping. One of the most important thing is that the planar regions do not lose their area when they are joined. They are non-overlapping. So this plays an important role. Without overlapping each other. Now here T is the total planar region which is obtained by region 1 plus region 2. Then I have a mathematical property which connects area of the whole total region T denoted by AR of T will be equal to area of the region P, that is the first region, plus area of the second region Q. So if I join the two regions, implies area of P plus area of Q equals area of the entire total region T. Is how I understand the total region. Area of T equals area of P plus area of Q. So T the total region which joins both P and Q, then area of the total region will be area of the two regions which are joined without overlapping each other, which plays a vital role. Non-overlapping planar regions denoted with mathematical equation AR of T equals AR of P plus AR of Q is how we understand the concept connected with planar regions. Now that we have discussed about planar regions and their areas, now comes the areas connected with different geometrical properties. Mostly we will see the figures which are on the same base and between the same parallels. That is, if I observe and investigate the two objects which are the two figures which are on the same base and between the same parallels, then what is the conclusion or the mathematical outcome which is made by investigating the figures between the same base and between the same parallels is what we are going to see for today's session. So today's session is about figures on the same base and between same parallels. So let's see in brief the figures on the same base and between same parallels. For example, let me take an example case. Say I have the same base AB. Now as the concept says about same base, let me take the same base AB and let me take the two parallel lines with the base. So I have a parallel, this is parallel to this. So I have a line L which is parallel to the base AB. Now it says that any figure you take on the same base and between same parallels will have certain geometrical properties. So let's see what are the geometrical properties connected with two figures on the same base and between same parallels. For example, let me take a triangle which connects out here. Suppose I draw a triangle with the base AB, and let's see the figure 1 which is obtained by drawing a triangle. Let C be the point from the parallel line where a triangle is formed. Let me take another point D where I would draw a triangle provided with the same base. So between the same parallels AB and the line L, I have a triangle ABC with the base AB. Now I will draw a triangle ADB with the same parallel. Now here comes the investigation on what would be the relation between this triangle ABC and this triangle ADB. So here we are going to investigate the figures on the same base and between same parallels. So in this case, triangle ABC and triangle ABD are the figures on the same base and between same parallels. So triangle ABC and ABD are said to be the two figures or the two triangles on the same base and between same parallels. Here AB, which is the same base for these two triangles, and the parallel lines are the base AB which is parallel to the line L, is how we see the parallels. So these are the two figures, for example, when I take are the two figures between same bases and same parallels. So triangle ABC and triangle ABD are the figures on the same base and between same parallels. Is how we can take many examples in mathematics where we can take two figures between same base and between same parallels. This being one of the example. Let me take another example to understand the concept more better, to be continued with. Now here, let me take the base AB and let me take a line which is parallel to this. Now AB is the same base, and let me take two points C and D where ABCD is a parallelogram, and let me take a point E such that there are two figures formed between the same base AB and between these two parallels, that is, one of them being this parallelogram and this being a triangle. So ABC is the triangle and ABCD, ABE is the triangle and ABCD is a parallelogram, which are on the same base AB and between the same parallels. So here AB is the same base and L is parallel to the common base AB, then triangle ABE and parallelogram ABCD are the two figures which are on the same base and between same parallels. So here note that this and this are the figures on the same base and between same parallels. This is how I understand the concept of two figures with the same base and between same parallels. This being one of the example case. Triangle and a parallelogram on the same base and between same parallels. Now let's take an example case where the triangle or the two figures are not between same parallels to understand the concept more better. For example, I take the same base AB and I take a parallel line L which is parallel to this. Now here let's connect say I have a point C which makes the region ABC. This is one of my region. Next comes say another region in which I have a point D which connects with B. With this. So have another triangle with the shaded region out here. So here let me say I have a point D which is exactly out here. Therefore, I have a point D which is down this exactly but not touching the line L out here, the line which is parallel to this. So in this case, I see that the triangle ABC is on the same base AB and triangle ABD also is with the same base AB, but they are not between same parallels because ABC is a triangle between parallels with the third vertex C exactly on the parallel line. But this point D is not on the parallel line and hence it is slightly below. This region cannot be between same parallels. So I come to the conclusion that since point D is not on the line L which is parallel to AB, therefore though the two figures triangle ABC and the second figure triangle ABD, though triangle ABC and triangle ABD are on the same base, are not between same parallels L and AB, is how I understand this exclusive problem. Triangle ABC is between the same base and between the same parallels, but triangle ABD is on the same base AB but not between the same parallels. This region is left out, is how I understand that the two regions are said to be between the same parallels if their remaining vertices other than the base entirely lie on the parallel lines. So here the remaining vertices other than the base here is C, so this must entirely lie on the line L, which is parallel to AB. Here the remaining vertex D other than the base AB must lie entirely on L, but since the point D does not lie on the line L, which is parallel to AB, therefore it is not between same parallels, but it is between the same base AB, is how I understand the two figures are on the same base and between same parallels if the figure has its vertices other than the base which lie entirely on the line which is parallel to the base, is how we conclude with figures on the same base and between same parallels. Now that we have defined and understood two figures on the same base and between same parallels, now comes the discussion of using the two figures on the same base and between same parallels for the learned concepts. I'm talking about the parallelograms. So let's investigate on the two parallelograms which are on the same base and between same parallels. Let's see what would be the learning outcome or the conclusion drawn out of the investigation. So today's session is about parallelograms on the same base and between same parallels. Parallelograms on the same base and between same parallels. So let's take the parallelograms on the same base and between same parallels. Let the base be AB out here. Let there be a line L which is parallel to the base AB. Now here, let me take two parallelograms. This is the parallelogram on the base AB, say C and D. Let me take another parallelogram. E and F. So here I have two parallelograms. One is the parallelogram which is obtained by ABCD. is the parallelogram, and the other parallelogram is this. Out here. So the two parallelograms are ABCD and ABEF, which are on the same base AB and between the parallel lines L and AB. So here figure ABCD and figure ABEF are the parallelograms on the same base and between same parallels. Are parallelograms on the same base and between same parallels. The same base here being AB. And the parallel lines are L and AB. So let's see what is the property which connects the two parallelograms ABCD and ABEF, which are on the same base and between the same parallels. Property which connects is parallelograms which are on the same base, and between same parallels are equal in area, is how I understand the property. The property says that if the two parallelograms lie on the same base and between same parallels, any two parallelograms lying between two parallel lines and lying with the same base must be equal in area. So area of this parallelogram is equal to area of the second parallelogram in this diagram, is what is the property which defines in mathematics. So area of this parallelogram, therefore area of parallelogram ABCD is equal to area of parallelogram ABEF. This is how I understand the area of two parallelograms being equal when they are on the same base and between same parallels. This holds for any two parallelograms using the two properties connected. Now that we have discussed about the properties related to parallelograms or any two figures on the same base and between same parallels are always equal in area. So in the previous session, we have seen two parallelograms which are on the same base and between same parallels are of same equal area, however far or however near they are between the parallel lines. But the condition, the base must be same and they must be between two parallel lines. Now let's see if the converse holds true. Given that two parallelograms lie on the same base and given that the two parallelograms are of equal area, now the investigation comes on whether these two parallelograms lie between same parallels. So let's see if the condition of same base and equal areas of parallelograms gives the learning outcome that they are between parallel lines, or that the outcome conclusion is that they must be between parallel lines. So let's see in brief. Before we see the investigation of the converse of the previous theorem, now comes the introduction of area of parallelogram. So let's see area of parallelogram. The area of the planar region called a parallelogram. Opposite sides parallel and equal. Area of parallelogram. What is area of parallelogram? Just like area of triangle is half into base into height, and area of rectangle is length into width. Similarly, area of parallelogram has its own specific definition. Let's see what is the formula we can derive for area of parallelogram. So let me take a parallelogram ABCD. Out here. So here is my parallelogram A, B, C and D. And let me drop a perpendicular from D such that this forms perpendicular and this is the height of the parallelogram. So this is called the height of the parallelogram. So in parallelogram ABCD, the symbol for parallelogram is this. So in parallelogram ABCD, now I take the base which is on the bottom of the parallelogram, that is AB is the base of this parallelogram. AB is the base, is how I understand the base being AB. So let me denote the base with some B units. Now comes DE. What is DE? So here from D, drop a perpendicular to AB. So from D, if I drop a perpendicular to AB, which cuts AB at E, which cuts AB at the point E. Now clearly we know that DE is the perpendicular, that is DE is the height of the parallelogram. So AB is the base of the parallelogram and DE is the height of the parallelogram. So base denoted by B, of course, height now denoted by H. So we have the base and the height for the parallelogram ABCD. So AB is the base and DE is the height. B stands for base and H stands for height. Now let's see the area of the parallelogram. So here we have a formula which says area of parallelogram ABCD. It can be meter square, it can be centimeter square, it can be kilometer square. Now let's come back to the converse of the previous property. Triangles on the same base and between same parallels are equal in areas. And parallelograms on the same base and between same parallels are equal in areas. Now the converse of that theorem. So how do we define the converse? So let's state the converse. My question is, will parallelograms on the same base, which are on the same base and having equal areas, the two parallelograms or any number of parallelograms on the same base and having equal areas lie between is what I have a question as converse. Will parallelograms on the same base and having equal areas lie between the same parallel lines? Is the biggest question out here. So let's see the converse of the previous theorem. Investigating the converse of same bases and same parallels. Now, let's take two parallelograms with the same base and lying between two lines which are not parallel. So the converse clearly says that if I have the same base AB and if I have two parallelograms lying, let me say there's another line L which is not parallel to this but a bit away from the base AB. Now let me take two parallelograms in this case. So one of the parallelogram is formed by the line L, which is A, B, C and D. So A, B, C, D is a parallelogram which is formed with the base AB and the line L. So here is the parallelogram. Now with this parallelogram, let me take another parallelogram which has the same equal area. The condition for converse is that they lie on the same base. So taking the same base AB, I'll draw another parallelogram which has equal areas and same base. So let me take another parallelogram of the same equal area between the line L and the line AB, the same base AB. So here is the same base AB. This is the same base. So therefore, I take another parallelogram out here, AB, EF. So here I have another parallelogram AB, ABEF out here. So here is the parallelogram ABEF between the same base AB and between the line L and the base AB with equal area. So here ABCD and ABEF are the parallelograms on the same base AB, which is out here, are parallelograms on the same base AB and between the lines L and same base and between the line L and same base AB. So between same base and the line, there are two parallelograms ABCD and ABEF which are equal. Also, area of parallelogram ABCD equals area of the other parallelogram, which is ABEF. So area of parallelogram ABCD is equal to area of parallelogram ABEF. So we have taken parallelograms having equal areas as per the converse of the statement. Now, when in such case of two parallelograms lying on the same base and with equal areas, will the lines be parallel? Is the question out here. The converse of the theorem clearly says, as supported by mathematics, that they must be parallel. Two parallelograms lying on the same base and which are in equal area must be between the parallel lines. That is, this must be equal to this. Is how we understand the converse of the theorem. So here, that implies the line L is parallel to the base AB. So we have a property which says triangles, parallelograms on the same base and with equal areas must lie between the parallel lines. That's how we understand the converse of the previous theorem. Converse holds true in this concept. Two parallelograms between two parallel lines. Now that we have discussed a property relating to the parallelograms, parallelograms on the same base and between same parallels are equal in areas and even the converse holding true. Now comes the question, what happens if I take the case of a triangle? Triangles on the same base and between same parallels, will the areas be equal? Is what we are going to investigate. The same theorem now investigated for triangles on the same base and between the parallel lines. Let's investigate the property for triangles. Before we do that, let's understand the triangles which lie on the same base. Let's try to just recap with what we have learned. Triangles on the same base. So here, let me try to understand how the triangles look between the same base and between same parallels. Imagine I take the same base, which is AB, just like in the previous case of a parallelogram. So with the same base AB and between the parallel line L, let's say this line is parallel to the same base AB. Now let me draw two triangles which are with the same base AB and which are between the parallel lines. So here I have a triangle, say from here to here. That's how I get one triangle which is like this. So this is the triangle, the first triangle which connects the line L with point C. So ABC is a triangle with the same base AB and between the parallel line L and AB. So let me take one more triangle in the similar manner. Let me take a triangle which is far away. So this is out here. So I have the other triangle which connects with D. So this is the triangle ABD, which is on the other side. Now as we see the two triangles, this triangle is on the base AB and the other triangle also on the same base AB. So here AB acts as the same base and they are between the parallel lines L and AB. These two lines are parallel. So triangles on the same base and between same parallels look like this. Now the investigation comes to prove whether area of this and area of this are equal. So we are going to see how we can connect the areas of these two triangles which are on the same base and between same parallels, investigating the property for triangles. So let's see the property. So triangles on the same base. So if I take the statement for same base theorem says that triangles on the same base and between same parallels are equal in area is how we understand the same base theorem. So same base theorem says that if two triangles are taken on the same base and between same parallels, they are equal in area is how we understand the same base theorem connected with the property. So when I take two triangles between same base and same parallels, just like this, A, B, this is the line L, and I have a triangle like this, then the two triangles must have equal areas. So area of this triangle must be equal to area of this triangle is how we understand the areas. That is, AB being the same base, if AB is the same base, and L is parallel to AB, if the two lines are parallel and L is parallel to AB, then area of triangle ABC must be equal to area of triangle ABT. The area of the first triangle must be equal to area of the second triangle. Is how we understand the area of two triangles being equal when they are on the same base and between the same parallels. Is how we understand the property of two triangles with the same areas between same base and between same parallel lines. Now that we have discussed the property of two triangles on the same base and between same parallels are equal in area, now comes the question, what if there are more than two triangles? Well, all the three triangles will have equal area. Today's session is about triangles on the same base with the question, what if there are infinite triangles? What could be the case if I draw more than two triangles? Will all the areas be equal? Let's investigate with the property. So now that it is based on more than two triangles, let's take the case of at least 3 or 4 triangles between the same base and between the same parallels. So here I have the base AB and there's a line which is parallel to this. Now between the same parallels with the same base AB, let me take more than two triangles. Say for example, just like in the previous case, we have taken two triangles. Now I take many triangles between. Triangle number 2, triangle number 3, triangle number 4. So here I have totally 4 triangles as given by this. The first triangle is ABC. So totally I have 4 triangles which are taken with the same base to be listed out here. The first triangle is ABC. And the second triangle is ABD, as can be seen in the diagram. And the third triangle is ABE, as seen out here. And the fourth triangle is ABF, as taken here. So these are the 4 triangles which I have taken with the same base AB and between the parallels L and AB. So we have more than 2 triangles, that is 4 triangles out here with the same base AB. Interestingly, for all these, AB is the common base for all the 4 triangles considered. So according to the property, 2 triangles on the same base and between same parallels are equal in area. So when I take the first 2 triangles, the triangle area of triangle ABC must be equal to area of triangle ABD. Now when I take the case of the second and the third triangle, these 2 triangles are on the same base and between same parallels. So area of this must be equal to area of this. So with the second case, area of triangle ABD is equal to area of triangle ABE. Next, now since these 2 triangles are on the same base and between same parallels, ABE and ABF must have equal areas, as seen with 2 triangles on the same base and between same parallels are equal in area. The property as discussed in the previous session. Therefore, area of triangle ABE equals area of triangle ABF is what we see when I take the first 2 in pairs, then the second 2 in pairs, then the last 2 in pairs. So I have totally 3 pairs which define areas of each triangles being equal. Now that each of the triangles are equal, when I combine all these 6 possibilities, triangle ABC equals triangle ABD, which in turn equals this, which in turn this equals this. Therefore, area of triangle ABC must be equal to area of triangle ABD, but area of triangle ABD which in turn equals area of triangle ABE, and ABE equals ABF. Is how I see area of each of the triangles being equal. Therefore, if I have more than 2 triangles on the same base and between same parallels, all the triangles must have equal area, is how we understand the concept. So even if there are infinitely many triangles, they have equal areas if they are on the same base and are between same parallels. It's not restricted to two triangles, but more than two. It can be infinitely many triangles which can connect the same base with the line points on the line L, where all the areas will be equal, is how we understand. Infinitely many triangles on the same base and between same parallels are all equal in area, is how we conclude through the property. Now let's see area of triangle. What could be the formula for area of triangle? Just like area of rectangle is length into width, and area of parallelogram, which was recently proved as breadth into height or base into height, half. So we had area of parallelogram as base into height. Similarly, let's see area of triangle ABC. Triangle with its area. Area of triangle. Area of triangle is what we are going to investigate in the session. So let me take a triangle ABC. So ABC is a triangle. Now in this triangle, clearly I know that this is the base. And next, let me drop a perpendicular from C to AB, such that it cuts AB at D. So here the CD is the perpendicular which is called height. So this is the base and this is the height. So let's see how we can connect the base and height with area of triangle. In triangle ABC, AB is the base. And let me denote the base with some B. Denoted with B. And then I have CD, which is obtained by dropping a perpendicular from C. Drop a perpendicular from C to AB, such that it cuts at D. Therefore, here CD is the height, as clearly we can see. It is the height or the altitude of the triangle ABC. So I have base, which is denoted by B, and my height, which is denoted by H. So using the base and height, let's derive the formula for area of triangle. So with this being the base and this, I have my AB equals B and my CD, which equals H. Therefore, I can derive the formula as area of triangle ABC is given by the formula half into base into height square units. This is how we derive the formula for with the units unit square. So half into base into height is the formula for area of triangle, which can be reduced as half BH, because my base is B and my height is H, is how we denote with half BH unit squared. is what we get when we derive area of triangle ABC with the base B and the height h is half into base into height. So area of triangle is half base height. Is how we understand the area of the planar region triangle, a three-sided closed region. Now let's get back to the previous same base theorem as discussed for triangles. The statement which says triangles on the same base and between same parallels are equal in area. Now the question comes, what would be the converse of the previous theorem? Will the converse hold? Is the biggest question. That is, if I say triangles which are on the same base and which have equal area, will the two triangles lie between the same parallel lines? Is what we are going to investigate in this session. Triangles connected with converse of the same base theorem. So let's see the converse. So my question which arises in the converse is, will the triangles on the same base and having equal areas lie between the same parallels? Is the biggest question I have here. So my arising question here for the converse is, will the triangles on the same base and having equal areas lie between same parallels? So with the condition that they lie on same base and they have equal areas, will the two triangles be between parallel lines? Is what we are going to investigate in the process. So let's see how we can understand this concept. Imagine I have the same base AB, and let me take a line L which is parallel to AB. Now let's take two triangles which are on the same base and having exactly equal area. So the planar region of the first triangle, let me take the triangle out here, and let me take the other triangle out here, which are on the same base AB. So here is the same base and they are the same parallel lines. But now the converse says, but they are in the converse, they are not parallel, but they are on the same base AB. So we have the same base, and the other condition is that the areas are equal. It is about proving that the two lines are parallel. So now we are going to investigate on whether the line L is parallel to AB. So in order that we have the same base, let's take this triangle the first triangle ABC, and the second triangle is ABD. Okay. So here the condition is that AB is the same base for triangles ABC and triangle ABD. So AB is the same base for triangle ABC and triangle ABD. Also, area of triangle ABC is equal to area of triangle ABD. These two triangles are considered in such a manner that they have equal area. Therefore, the two triangles chosen here must have equal areas. So with these two conditions, let's see if the two lines are parallel. Therefore, Converse states that L must be parallel to AB. So if the two triangles are with the same base and which are having equal area, they must lie between the two parallel lines, is what the converse says. So converse of the same base theorem is true to its justification. Converse holds for same base theorem. That implies converse holds true, is how we understand. So therefore, the triangles which are on the same base and having equal areas must lie between same parallels. They must be parallel. L parallel to AB, the same base, is how we understand the converse and its conclusion. Now that we have discussed the same base theorem on triangles and its converse, now comes the question on applications of same base theorem in solving many math problems. Today's session is about applications of same base theorem in real life. Applications of same base theorem. So let's see in brief about the applications of same base theorem. So here my question comes, find the area of the triangle ABD for the following diagram. So here I have a diagram in which I had to find area of triangle ABD. So let's see how we can find the area for the given problem. So here I have a diagram . Now here I had to find area of triangle ABD as clearly seen in the diagram. It is given with area of triangle with the dotted region is centimeters square. Now area of triangle ABC is given to be 14.6 centimeters square. That is given area of triangle ABC is 14.6 centimeter square, and AB is the same base. So clearly I can see that triangle ABC and triangle ABD are on the same base. So here is the same base. And also they are between same parallels. So identify here that AB is the same base. AB being same base, and the two triangles are between same parallels L and AB. Also, the line L is parallel to the same base. Same parallels. Now, striking with the previous same base theorem, these two are the two triangles which are on the same base and between same parallels. That is, therefore, triangle ABC and triangle ABD are the triangles on the same base and between same parallels. So triangle ABC and triangle ABD are triangles on the same base and between same parallels. Therefore, by same base theorem, we have area of triangles are equal. Triangles on the same base and between same parallels are equal in area. Therefore, area of this triangle must be equal to area of the second triangle. Area of triangle ABD or area of triangle ABC is equal to area of triangle ABD, are the two triangles which have equal areas. Therefore, I have this with area of triangle ABC, which is 14.6 centimeters square. So I have substituted for triangle ABC with 14.6 centimeters square. So 14.6 centimeters square is the area of triangle ABC, which indirectly states that the area of triangle ABD is 14.6 centimeters square, substituted with this. Therefore, the given question is to find area of triangle ABD. Therefore, triangle ADB has the area 14.6 centimeter square. Therefore, I can find the area of the other triangle using the area of the given triangle by using same base theorem. Same base theorem helps me in applying the concept in real life. As in the case of this example, I wanted to find area of this triangle, and I could do the area of this triangle by simply taking same base theorem. So my same base theorem gives me exactly the equal area as that of the previous, because two triangles on the same base and between same parallels are equal in area, and hence area of triangle ABD is equal to area of triangle ABC with 14.6 centimeters square. Therefore, the value of the area of this planar region ABD equals 14.6 centimeters square. Is how we understand the application of same base theorem in real life connected with same base theorem. Now that we have discussed the same base theorem for triangles and the same base theorem for parallelograms, now here comes even the applications which have been discussed further. Now comes the concept of combining a triangle and a parallelogram. Now let's investigate what if there is a triangle and a parallelogram with the same base and between the same parallels? How do we connect a parallelogram and a triangle is how we're going to discuss in the session. Same base theorem for triangle and parallelogram. Connecting triangle and parallelogram. Same base theorem. So let's see how we can connect a triangle and a parallelogram with the same base theorem. So here, let's see how we can understand the triangle and a parallelogram in the same base initially before we understand the theorem connecting them. So for a triangle and parallelogram on the same base and between same parallels is understood as the common base AB and the parallel line L, which is parallel to this. And say I have a triangle out here, and next I have a parallelogram out here. ABC is the triangle and AB DE is a parallelogram. So here I have a parallelogram. So ABC is a triangle and ABDE is a parallelogram. So they are, of course, found to be on the same base and between the same parallels L and AB. Triangle ABC and parallelogram ABDE are on the same base AB, as can be seen here, and between the same parallels L and AB. That is the line L, which is parallel to AB, is how we understand a triangle and a parallelogram on the same base and between same parallels. Now comes the question on the investigation of the areas of the triangle ABC and the parallelogram ABDE. Will the areas be equal, or is there any relation which connects area of triangle with area of parallelogram is the biggest question. Let's investigate area connected with parallelogram and triangle on the same base and between same parallels. Now let's state the theorem. Same base theorem for a triangle and a parallelogram. So statement. A triangle and a parallelogram on the same base and between same parallels. If the triangle and a parallelogram are on the same base and between same parallels, makes the area of parallelogram to be twice that of the triangle. So in such a case, we see that area of parallelogram is twice that of area of triangle. It is not equal, but area of parallelogram is twice or double of the area of triangle. So the statement is very clear with its statement, which says a triangle and a parallelogram on the same base and between same parallels make the area of parallelogram to be twice that of the area of triangle. Is how we understand the connection between a triangle and a parallelogram when they are on the same base and between same parallels. Let's see the property in brief. Suppose I have a same base AB and I have a line L which is parallel to AB. Now, I have a triangle I have a parallelogram. So here is the parallelogram ABDE. So I have a triangle and a parallelogram between the same parallels and the same base. So here is the parallelogram. And here is the triangle. Is how we understand a triangle and a parallelogram on the same base AB and between the parallels L and AB. So the statement clearly says that for triangle ABC and for parallelogram ABDE, which are on the same base and between same parallels, area of parallelogram ABDE is twice of area of triangle ABC. That's how we understand the property of area of triangle and parallelogram. Why do you think is the area of parallelogram twice of area of triangle? How is the twice of the triangle connected? It's very simple, because a parallelogram is a four-sided figure obtained when its diagonal divides the parallelogram into two triangles. Say for example, I join the diagonal BE. So here I observe that there are two triangles between the diagonal, and we know that the two triangles are congruent in case of the parallelogram. A diagonal makes the two triangles to be congruent in a parallelogram is what we have learnt in the previous sessions. So if I have a diagonal, it makes area of this to be equal, or the diagonal bisects the diagonal of the parallelogram, divides the parallelogram into two equal areas. Is what we have learned in the previous session. And therefore, when I cut the diagonal BE, I get two triangles ABE and BDE in the parallelogram ABDE, whose areas are equal. Therefore, this area equals this implies this would be twice of the added areas. And therefore, when I add this area with this, exactly two triangles on the same base are equal. So area of this equals area of this equals area of this. So A equals A plus A, which is 2A. So area of triangle equals twice. Area of parallelogram is twice of area of triangle, is how we get when each of the areas are equal. So therefore, this could be with the possible area of triangle ABC, which is equal to area of triangle ABE, which is equal to area of triangle BDE. All three areas being equal is how we get the three areas equal in this. And therefore, area of parallelogram ABDE is twice area of ABE, because the diagonal makes the two triangles congruent in a parallelogram. These two areas divided by the diagonal are equal, which is nothing but 2 times of area of ABE, which is equal to ABC. Therefore, area of parallelogram ABDE is equal to twice area of triangle ABC. That is, area of parallelogram ABDE is double or twice of area of triangle ABC. Therefore, we come to the conclusion that if there is a triangle and a parallelogram on the same base and between same parallels, which there must be with the condition that area of parallelogram makes exactly twice the area of the triangle, is how we understand the property connecting the triangle and the parallelogram in the same base theorem. Triangle connected with parallelogram to the same base theorem.